This is the problem on the air conditioner, and it says a Cutnell air conditioner maintains the temperature in a house at 297 kelvins on a day when the temperature outside is 311 kelvins. What is the coefficient of performance of the air conditioner? Okay, what's given is the high temperature that is inside the house, 209, I'm sorry, that's outside the house, 311 kelvins, that's 38 degrees Celsius. Whoa, this is like 110 outside. And inside the house it's 297 kelvins or 297 kelvins, 24 Celsius, or in the neighborhood of 80 Fahrenheit inside the house. So the house itself is already pretty warm. But we need the Kelvin temperatures anyway, so I didn't have to convert them a moment ago, but I just did that to illustrate. Then we're supposed to figure out what the COP is, and we basically just have one equation in the book for the COP, and that one is the amount of heat that is being removed from the inside of the house. So let's see, in this diagram here, there's the exhaust heat going this way. Here's the heat going in, this one here. That's the heat being removed, and then the same air, of course, being pushed out, but now it's cooler. So that heat goes in here. Then there's electrical energy that moves that heat to the outside, and then the exhaust heat out here is that energy that is being removed from the house plus the work that is being inputted. So here's the work, and what I just said in mid-air was that the QH, the exhaust heat, equals the electrical work that is being put in plus the heat that is actually removed from the house. Okay, none of these we know. We don't know any of these. So what can we do with that? Well, here's one thing we can do. I'm going to write it as such that I only have QC's and QH's. So I'm going to have QC divided by QH minus QC. And now I go back to that one equation that says that a Cutnell engine is reversible, and therefore it can also be treated as that. This equation here can also be treated for an air conditioner or refrigerator or heat pump. So QC over QH, I'm going to use a different color, QC over QH is the same as TC over TH. And when I plug that in, I'm going to come up with this. So the COP equals TC over TH minus TC. And what I just did, that's not quite true. I shouldn't do that. But when I really do the algebra, then this is what happens. COP equals, for example, I can divide all of this here by QC, and then I'm going to have 1 divided by QH over QC. As long as I divide both the numerator and the denominator by the same number, I haven't changed anything. Now here I can plug in that TH over TC. There we go. And I think you can see that from here, going from here to here, I divided everything by QC. That of course gives me a 1 here and a 1 there, and then of course the fraction QH over QC. And here I used this one here, plugged in the temperatures, and now when I multiply everything again with TC, I come up with this expression that I kind of pulled out of thin air a moment ago, but it is correct because I just showed you the algebra. And then this one here is going to come out to with some number here with some coefficient of performance, and top of my head it's like somewhat over 10 as the coefficient of performance. That means you put in, let's say, 100 joules of electrical energy, and you're able to pump out 2000 joules of energy. That's what the COP means. Again, it has no units.